Here we go. We're going to embark on what is one of the more brilliant ideas over the years, certainly of modern times, that has ever been. In fact, it is known as that, as one of the most brilliant ideas ever to have occurred to human thought, which has allowed society to progress. That being the idea of calculus. But the idea is an idea of what's called an infinitesimal. I mean, you're familiar with the word infinity, of course, which is the biggest thing you can think of and then keep going. It's even bigger and bigger and bigger. And obviously you can't get there. An infinitesimal is the other end of the scale. Right? Doesn't matter how small you think of something, you can always divide it down, every measurement. An infinitesimal is when you can't divide it anymore. And obviously, just like you can't reach infinity, you can't get it down to that infinitesimal, because everything you could always go, oh, now I've got this, I'll divide it in half. But it was this idea of an infinitesimal that allowed us to deal with it. So we're going to develop it by looking at a problem. How do we find the slope of a tangent to a curve? So here's just some random curve, y equals function x. Now I know the equation of the curve and I know that point. But the question is, how do we work out the slope? Normally, to find a slope, I need 2 points on the line. I've only got 1 point on the line. But I do have the curve there. Okay? So I could estimate it by drawing a secant to that curve. So PQ would be an estimate for the slope. Obviously a lousy one, but it would be an estimate. So the question, therefore, is, where do we place Q to get the best possible estimate? And the answer is as close to P as possible. And so that's where this idea of an infinitesimal comes in. So if I could place it at an infinitesimally small distance, then in fact I'd end up with an exact value, because there's no distance between them. So let's just expand that out. There we go. We've now blown in. Okay. X is the point we know. So it's x and it's on the curve, so function x is its y value. Q is that infinitesimally, that's a hard word to say sometimes too, infinitesimally small point next to it. So x plus h is that tiny, tiny distance away from x. And so the y value would be whatever we get when we substitute that in, function x plus h. So the slope of PQ then, well, there's our slope formula. Function x plus h minus function x over h. Now there's the problem. Because remember, h we said is that infinitesimally small. So small it may as well be 0. But we know we can't have 0 on the bottom of a fraction. So that's where we use the idea of limits. Limits allows us to investigate what value it's approaching. So we can't actually get there. But if we could get there, what value would it be at? So the slope of the tangent can be exactly worked out, saying the limit as h approaches 0, so it's infinitesimally small, of function x plus h minus function x all over h. That is what we call the derivative. The derivative of y with respect to x. So in other words, when we think about it as slope, it's how's y changing as x is changing. It's a similar sort of an idea. Symbols that we use for it. Probably the most common one, dy dx. Now, where did that come from? Well, d probably evolved from delta, which you may remember in science we use, well, change, really small, that sort of thing. So that's probably where the d comes from. Y, well, some people call it y prime, some people call it y dash. F dash x, so whatever the function is with a dash. And this one here, it's still the idea of dy dx, but instead of writing y, writing what the actual function is. So d, whatever the function is, dx. So the derivative will measure the rate of something changing. So whilst we just investigated looking at the slope, anything that changes, we can use derivatives for. Now, that's why I say it was such a powerful idea, because the world is changing. Everything is changing. And so it allowed them to measure all these sorts of things. We see the beauty of it is because we were using a curve, but if we're infinitesimally small, the tangent and the curve are the same. It's like turning a curve into a straight line. And then once we've got it as a straight line, we can use all our coordinate geometry ideas. So here it is, written as a derivative, f dash x, the limit as h approaches 0, and so on. You might have heard of this expression, differentiating from first principles. So basically it means go from scratch. All you've got is the function, go from scratch, using your limits, get the answer. So let's pick a simple one. One we should know the answer to, of course, because remember it's representing the slope of the curve. So I've deliberately picked a straight line here because we know what the answer should be. Don't we? No good. Let's have a look. Function x is 6x plus 1. Well, function x plus h, sub in x plus h for x, 6x plus 6h plus 1. So limit as h approaches 0. And we've got a bit of tidying up to do. But on the top of the fraction, we get 6h over h, and we can use that idea of cancelling now. Because there is that problem of 0 on 0. Makes sense we get 0 on 0, because it's rise over run. But remember, we're saying the point's basically the same point. So the difference in the y values over the difference in the x values, of course, we've ended up with 0 over 0. But using limits, cancel the h's there, we get an exact value of 6. Because there's now nowhere to substitute the h into. So there's the slope, 6. So if I wanted to find the equation of a tangent at the particular point, obviously the equation of the tangent is going to change depending on which point, and the slope of the tangent will change. This is a parabola, but on the parabola it's changing all the way too. We want to locate the actual slope at 1. Function x, x squared minus 5x plus 2. Function x plus h, everywhere I see an x, put in an x plus h. So my derivative, I've just expanded out there. Nothing actually tidied up there. Function x plus h minus function x. What you'll find with these polynomials anyway is that everything will cancel unless it has an h in it. So it works out quite nicely because then it'll cancel with the h in the bottom. But anything that doesn't have an h, you should find cancelling. So you've got the x squared minus the x squared, you've got the 5x minus the 5x, and the 2 minus 2. Now we can divide everything by h. And we have 2x plus h minus 5. So as h approaches 0, that expression is 2x minus 5. Now that is not the slope of the tangent. A lot of people mistakenly think, oh, that's the slope of the tangent. No, it's the formula that allows you to find the slope of the tangent. You can actually physically substitute in to get the slope. So we want to know when x equals 1. So when x equals 1, dy dx is minus 3. That's the slope of the tangent. And if I want to find the equation, point slope formula. And there it is, y equals minus 3x plus 1 for that particular curve. 7b, 3, not IV. Don't know why not. 12, just h approaches 0.